Hello students, let us continue the discussion on moving charges and magnetism. In the last session we discussed about galvanometer, moving coil galvanometer, the exact construction, working mechanism, everything we discussed. When current flows through it, the coil generates the magnetic field, and that magnetic field, upon interacting with the external magnetic field, it experiences a torque. A spring is kept to generate reverse torque, or which is also called restoring torque, and hence we see the deflection, proper deflection for certain amount of current flowing through the coil. So now moving ahead, we'll see, because galvanometer is something which is not applicable, which cannot be used to measure the current actually, because the reason being, galvanometers are so much sensitive that, and we also discussed about current sensitivity and voltage sensitivity, right? See, here we have a galvanometer, uh, okay, with 30 deflections, okay, 30 divisions, and each division will read 20 microampere of current, okay, 20 microampere. So now you can imagine it is 600 microampere of current, okay, which is 0.6 milliampere, okay, 0.6 milliampere of current can be measured using this galvanometer, okay. So it's only 0.6 milliampere of current which can be measured using this galvanometer, because the galvanometer is that sensitive. So, but now I might be in a situation to measure say 1 ampere, 2 ampere current and all. How do we measure that? This gets over, or the deflection is completes for just 0.6 milliampere of current. But I want to measure 2 ampere of current, which is somewhat like thousands times greater than the total current that can be measured using this galvanometer. So now there should be another instrument which shall be used to measure larger currents. Okay, so uh, galvanometer is actually used just to get to know what is the get to know the presence of current, but the device which is used to measure current in the circuit is called ammeter, right? Ammeter is the device which is used to measure the current in the circuit. So now, as similar to galvanometer, we should now understand the construction and working of ammeter also, because that's an electrical measuring device which measures current in the circuit. So now we'll understand how the construction of and working of ammeter is. Uh, so the basic idea that we are going to employ here is the galvanometer itself. We will make use of a galvanometer itself, but we will convert that galvanometer into ammeter. We will also convert the same galvanometer into voltmeter, which is used to measure the potential difference. First, we will understand how to convert a galvanometer into ammeter. Okay, so the topic today is about conversion of galvanometer, into voltmeter. Okay, so now we are going to convert, or we'll study how to convert a galvanometer into voltmeter. Sorry, not voltmeter, ammeter. Into ammeter, right? So first we will take the galvanometer itself. Okay, the basic idea is galvanometer with certain resistance, higher or larger or lower. Okay, higher resistance or lower resistance, either connected in series or connected in parallel with the galvanometer. Okay, that's the basic frame. Now let us look into the exact conversion. See, first we should understand that an ammeter is always connected in series with the regular circuit, right? If this is the circuit through which the current is flowing, I be the current which is flowing through the ammeter, flowing in the circuit, so ammeter is always connected in series. So if you want to have the complete picture, say this is the resistor and this is the battery. Now if you want to measure the current through this resistor, we connect the ammeter here, right, in series with the resistor. That will give us the value of current. So keep that in mind. Ammeter is always connected in series. Ammeter as a whole device is connected in series in the circuit to get the current in the circuit. Let I be the current flowing through the circuit. Okay. Now what we are going to look is what exactly this ammeter look like inside it. Okay. What is the exact arrangement of different components inside ammeter. Okay. Inside ammeter, what we will have is a regular galvanometer. Okay, a regular galvanometer. So, say I am going to expand this part here. Okay, a regular galvanometer to which a low resistance. Okay, a low resistance is connected in parallel. That low resistance connected in parallel is named as shunt. S-H-U-N-T. Shunt. So what is shunt? Shunt is a low resistance connected in parallel with the galvanometer for the conversion of galvanometer into ammeter. Okay. So this ammeter inside looks like this. Okay. So that is how we convert a galvanometer into ammeter. A galvanometer is converted into ammeter by connecting a low resistance called shunt in parallel with the galvanometer. Now the question that comes is, why do we need to connect it in parallel itself? The reason being, galvanometer will have its own resistance, right? So the basic intention here is we should not take out too much current from the main circuit. Okay, we should keep the current in the main circuit as it is. Okay, almost the same. It's not possible to keep it completely the same, but we will always try to keep the main current in the circuit remains the same, and we'll draw very small current to get the reading in the galvanometer. Okay, see now what happens is, just try to imagine I is the total current flowing through the ammeter. This together, everything is ammeter now. So this current I splits from this point. Okay, splits from this point, and say Ig is the current that flows through the galvanometer, and the remaining current of I, which will be I minus Ig will flow through the shunt resistance, and hence the current will become I again and flow through the circuit. Clear? I is the total current entering the ammeter. Inside the ammeter, Ig, part of this I, which is Ig, will flow through the galvanometer, and the remaining current I minus Ig will flow through the shunt resistance. So now, if this resistance is of higher value, then what happens is most of the current in the circuit. Okay, see the main current in the circuit is I, and we don't want too much current in the galvanometer, right? Because if we have too much current, okay, because as you observe now, the galvanometer that we have can measure only 0.6 milliampere of current, 0.6 milliampere of current. Even if we have somewhat like 10 milliampere, 50 milliampere, this cannot show the exact reading, isn't it? Along with that, if it is too much of current flowing, like 1 ampere, 10 ampere and all, then the galvanometer will get damaged. So we need as less current as possible to flow through the galvanometer. What is the way to do so? We need to bypass most of the current through another path. That is why we connect a shunt resistance here. This is a very small resistance, and hence most of the current, okay, not all the current, most of the current will flow through the shunt resistance, and a very small current will flow through the galvanometer, and hence the galvanometer will show proper deflection. Clear with this? So now let I be the maximum current that has to be measured. Okay, what is I there? I is the maximum current that has to be measured. Okay. Next, what do you mean by that? Which means now, as I said, I want to measure 2 ampere of current. Okay, then I itself is equal to 2. Okay, the range that I want, the maximum range of current that I need to measure, let that be I. Okay, which is 2 ampere for my example that I have considered now. Then what is Ig? Ig is the current which will flow through the galvanometer. So Ig is the maximum current required for the full scale deflection of galvanometer. Okay. So for this particular galvanometer, Ig is 0.6 milliampere, isn't it? Because Ig is the current for which the galvanometer shows full scale deflection. After that, the deflection is done. It's always exceeding the deflection. So Ig is the current for full scale deflection of galvanometer. Following. Next part of that, I minus Ig will flow through the shunt resistance and will go there. And now we will have different kind of ammeter based on our requirement. Few ammeter will be somewhat like in the range of 50 milliampere or 10 milliampere. Few of them are somewhat like 2 ampere range. Okay, which means the maximum current that can flow through the part of the circuit that we choose can be any different current depending on the experiment that we do. Sometimes it's only in terms of 50 milliampere, 100 milliampere, 200 milliampere which flows through the circuit. And sometimes it is 1 ampere, 2 ampere that flows through the circuit. So depending on the experiment that we have chosen, we will need different ammeters here. Which means, what do you mean by different ammeters? Which means that we should have ammeters of different range. So if the current flowing through this is somewhat like 50 milliampere, 55 milliampere, 60 milliampere and all, I need an ammeter of milliamperes range. Okay, milliamperes range. If the current flowing through it is of 1 ampere, 2 ampere and all, then I need ampere, 1 ampere or 2 ampere ranged ammeters. Let me show you different ammeters depending on the requirement. See, now I have 2 ammeters with me. Okay, this is milliammeter which has the range of 500, which means this can read, okay, the maximum current this ammeter can read is 500 milliampere. Okay, so this is used when the current in the circuit is in terms of say 100 milliampere, 200 milliampere, 250 milliampere. If the current is in that range, we will make use of this. Now, if the current is more than that, we will make use of this. Look at this. This is a regular ammeter, not milliammeter, ammeter. Okay, the range of this ammeter is 2 ampere. Okay, 2 ampere, which means if the current flowing through the circuit is 1.5 ampere, 1.8 ampere, or 2 ampere, 1.6 ampere, and all, then we will make use of this ammeter for that purpose to measure it. Okay, so now what is varying here? The maximum current through the circuit or the range of the ammeter that should be chosen is varying, which itself is our I. Okay, so now what will decide decide the current that can be measured? This shunt resistance, okay, the low resistance connected here will decide the range of ammeter that we have chosen or the value of I. Okay, so now let us work for the relation between S and I, because that is what is very important. See, how do I make those two kinds of ammeter, milliammeter or regular ammeter? By choosing a particular value of S, that's it, nothing else. Okay, for different values of S, I get different range of ammeters. Following? So now if I get a relation between I, the maximum current that we need to measure, and S, then we can choose the shunt resistance for a particular ammeter that we need to design. Okay, so let me take the formula of that or the relation between I and S now. Right, let me before that let me apply let me take the resistance, the internal resistance of the galvanometer as G itself. Okay, We all know that galvanometer will have its own resistance. Wheatstone's bridge, we have already discussed about it. So applying a KVL for the loop, okay, I can apply KVL for this loop, or I can even take the potential difference as common, that's also fine, okay, both are fine. Let me name it and apply the KVL itself. Let me name it as A, B, C, D. Now applying KVL for the loop A, B, C, D, A. Okay. From A to B, current is Ig, resistance is G. So it is Ig, G, positive. And from C to D, it is minus of, because current is in the opposite direction, minus of I minus Ig times the resistance S is equal to no EMF in the loop is equal to 0. So taking that into the other side, I need the expression of I, right, expressed in terms of S. So, or expression for S in terms of I, that's also fine. Let me take the expression for S. S becomes equal to, look at this, Ig minus Igg goes to the other side, becomes positive, this becomes positive, that's fine. Divided by I minus Ig, right. So this gives us the expression for the shunt resistance that I need to connect in order to get a ammeter of range I ampere. Okay. So if I need an ampere of 2 amperes range, the maximum current 2 amperes, I need to simplify or substitute I is equal to 2 here. Okay. And Ig is the current for full scale deflection. What is Ig for this galvanometer? Ig for this galvanometer is 0.6 milliampere, right? Because it is 20 microampere for each division. So 30 divisions are there, which means this can measure for full scale deflection. It will take 600 microampere, which itself is 0.6 milliampere. So Ig we have, I is the actual current that we need to measure. In other words, it is the maximum range of the given ammeter, or maximum range of current that we need to measure. And G is the resistance of the galvanometer, S is the shunt resistance that we need to calculate. So now Ig is fixed, right? For a given galvanometer, Ig is fixed, the current for which the galvanometer shows maximum deflection is fixed. G is also fixed, which is the resistance of the galvanometer. And now this value of S and I are dependent on each other. If I decide certain current, I can choose certain proper shunt resistance, or if I decide particular shunt resistance, I can get the range of current that I need. Okay, they are interconnected, but the basic formula is we need to decide the shunt resistance which has to be connected depending on the range of current that we need to measure. Okay, so that is how we convert galvanometer into ammeter. So there comes a special case in this. The special case is an ideal ammeter. Okay, so how do you design an ideal ammeter? See, ideality means here, see, Ig is the current flowing through the galvanometer, right? I minus Ig will flow through the shunt resistance. What is the, see here, we need to reduce Ig as much as possible, which means there should be no loss of current when the actual current enters the circuit, right? Because here, if Ig enters the galvanometer, since it has certain resistance, here we can expect certain power loss, isn't it? When Ig flows through that, we can expect certain power loss. We need to make that power loss 0. Right, which means Ig should closely become or nearly should become equal to 0. How do we do that? We can do that by shorting these 2 points A and B. If I short these 2 points, the current will completely flow through this. In other words, I need to introduce the shunt resistance of 0 resistance. Okay, so that is the ideal situation. This is the end of derivation, okay, the concepts. This is a very important 3-mark question. For an ideal ammeter, how do we design ideal ammeter? Ideal ammeter shall be designed, okay. So there should be as less power loss as possible. So what I need to do is I should connect a shunt resistance, okay, shunt resistance of 0 ohm. That's it. That is the condition of ideal ammeter. Okay, and what is the effective resistance of the ammeter? See, if it is only galvanometer, the resistance is simply G. Now there is another resistor of of resistance S in parallel with that. So the effective resistance this time is the parallel combination of galvanometer and shunt resistance. So the effective resistance of the ammeter is R is equal to parallel combination. You all know that G S by G plus S, right? So this is the effective resistance of the given ammeter, where G is the resistance of galvanometer and S is the resistance of shunt resistance connected. Very simple, R1 R2 by R1 plus R2, because they are in parallel. Okay, so this is where the derivation stops, and those are the special cases and the other points. I hope you are clear with this. Okay, now it's your duty. Okay, I'll give you a task to measure shunt resistance for this particular situation. I'll show you these two. Show you galvanometer and ammeter here. See, I have a galvanometer. Okay, this galvanometer, the value of Ig for this galvanometer is, as I said, it is 0.6 milliampere, and the value of I, the maximum range of current that has to be measured, is 500 milliampere. 500 milliampere for this. So now I need to convert this galvanometer into this ammeter. Okay, following? How do I do that? By connecting a shunt resistance. You calculate what shunt resistance shall be connected in parallel, so that I convert this galvanometer into this milliammeter. Following? The data should be taken. You decide what is Ig. I've told you actually 0.6 milliampere. And what is I? I is the full scale deflection value of converted ammeter, which is 500 milliampere. Okay, make use of conversions properly. And what is G? G has to be known, right? G is the resistance of the galvanometer. Resistance of this galvanometer is given, which is 100 ohm. 100 ohm. Okay, 100 ohm. Make use of this data and get the value of S for this particular conversion. Okay, so that is about conversion of galvanometer into ammeter. Next, the other conversion. As I said, we are now going to discuss about conversion of the same galvanometer into voltmeter. Okay, what is voltmeter? Voltmeter is an electrical measuring device used to measure the potential difference across two terminals. Okay, so now we'll see how do we convert a galvanometer. Okay, conversion of galvanometer into voltmeter. Okay, potential difference. One which is used to measure voltage is voltmeter. That's it, nothing else. What is voltage? Voltage and potential difference, they are one and the same. You know that, right? Okay, now see, whenever we take voltmeter is always connected in parallel with between the 2 points where we need the potential difference. So if this is the situation, we always connect voltmeter in parallel with the resistance to get the potential difference or voltage across the resistor here. Okay, so we'll connect it in parallel always. So as a single device, the voltmeter is always connected in parallel like this, right? We all know that it looks like this. Right, now we'll see what is the internal structure and working mechanism of the voltmeter. So the basic device is again galvanometer, which is converted into voltmeter. Okay, this time the exact opposite way of conversion of galvanometer into ammeter. Okay, so here how do we convert a galvanometer into ammeter? A galvanometer is converted into uh, galvanometer is converted into voltmeter. Okay. Before that, see, as I said, if this is the external resistance, okay, a voltmeter is always connected in parallel like this, right? In parallel. So now a galvanometer is converted into voltmeter. Okay, so this part I am going to expand now. I am going to expand this part. A galvanometer is converted into voltmeter by connecting instead of low resistance, this time a high resistance in series with the galvanometer. Okay, how do we convert it into ammeter? Low resistance in parallel. For the conversion of galvanometer into voltmeter in a high resistance in series. Okay, there it is low resistance, here it is high resistance. There it is connected in parallel, here it is connected in series. Okay, a galvanometer is converted into voltmeter by connecting a high resistance, say R, in series with the given galvanometer. So this entire structure together, the components together is a voltmeter now. Okay, this is how voltmeter looks inside it. Okay, and this is always connected across the main circuit, right? So this is where the main circuit will be, and this is where we are going to measure the voltage across these 2 points. Okay, that's good. And now let V be the total potential difference or the total voltage that has to be measured using this voltmeter. Okay, V be the voltage. For example, let me show you a voltmeter here. So here I have a voltmeter of range 2 volt. Okay, V is the symbol, 2 volt is the maximum voltage that I can measure using this voltmeter. As similar to this, we have different voltmeters of different ranges. Some we have in millivolt, some we have till 10 volt, 20 volt, some even we have till 100 volt. Okay, so depending on the resistance that we connect here, we can decide the value of maximum voltage that has to be measured using this galvanometer. And similarly, let Ig be the current flowing through the voltmeter. Voltmeter means current flowing through both galvanometer and the external and the resistance, high resistance connected in series, right? Ig is the same current that flows through this, like this, and V is the potential difference across these 2 points, this point and this point. So now, how do we convert? Basically, that you should make out. Okay, write it. Galvanometer is converted into voltmeter by connecting a high resistance in series with the galvanometer. Okay, normally this part of the circuit will not be considered. Okay, it's only this part of the circuit which will be considered for the interpretation. And now we will see the math part of it. Or see, now the value of R, capital R, decides V. What is V? V is the maximum voltage which has to be measured. Okay, maximum voltage has to be measured, or the range of voltage that has to be measured, 5 volt, 10 volt, the maximum one. For this voltmeter it is 2 volt, which I showed you. And G be the resistance of the galvanometer again. Okay, G is the resistance of the galvanometer. Ig is the current through the galvanometer. Okay. So now what is the now we need to get the relation between V and R, right? Because R decides V. In other words, for our requirement of V, we can decide R. If I need a 2 volt ranged voltmeter, I can decide what R I need. If I want, say, 50 millivolt ranged voltmeter, I can decide what value of R should be connected. Okay, so I need a relation which connects V and R. How do I get that? Simple, Ohm's law. What does Ohm's law say? V is equal to IR. I'll take Ohm's law from this point to this point. Let me name this point as A and this point as B. What is the total resistance between the points A and B? The total resistance between the point A and B, let me take that as, okay, I'll write it that directly. Total, or total is not the proper word, effective resistance, okay? Effective resistance between A and B. From here to there, we have two resistors in series, right? Is G plus R, right? G plus R is the total resistance or the effective resistance. So applying Ohm's law, okay? Applying Ohm's law between A and B, V is equal to IR. So V is equal to, current flowing is IG between two of the resistance in series, whose effective resistance is G plus R. That's it. We have an expression which can give us the relation between V and R, right? But what we need is R expressed, right? Because even in the previous derivation it was S, the value of S which we need to get, right? So from this G plus R is equal to V by IG, and G becomes equal to not G. G is fixed internal resistance of the galvanometer. R, the resistance that has to be connected in series, is equal to V by IG minus G. So this is the expression which will help us in deciding the value of resistance that has to be connected in series with the galvanometer, depending on what voltage we need to measure. Okay, P is the maximum voltage that we need to measure, and R is the resistance that has to be connected in series with the galvanometer to convert that galvanometer into the voltmeter of R requirement. Since you have the data now, I just showed you that I need to convert the galvanometer of 0.6 milliampere current range, okay, galvanometer's current range. For full scale deflection, IG is 0.6 milliampere. Now I need to convert that into a voltmeter of 2 volt range with the resistance of the galvanometer given G is equal to 120 ohm again, right? Make use of all those things and get me the value of R. Okay, right. So this is the end of the derivation and explanation of converting galvanometer into voltmeter. And now coming into the case of ideal voltmeter. Okay, what resistance should be connected here to make this voltmeter as ideal voltmeter? See, there will be certain current flowing in the main current through this resistor, right? The external part of the voltmeter. This is outside voltmeter. Okay. Now, if I take too much of current into this part, into the voltmeter, this will not be fed with the proper amount of current. So I need as less possible current flowing through this part, this branch or this part of the circuit. How do I make that? G is fixed. I can increase R, the external resistance that I am connecting, converting resistance that I am connecting. I can increase R. So if I increase R, less current will be entering this branch, isn't it? More current will be flowing through this. And if I make R infinity, for the ideal situation, if I make R equal to infinity, most of the current or all of the current will flow through this part itself, and very less or zero current will flow through. You can ask, what if zero current flows through, galvanometer will not show any deflection at all? Those things are fine, but this is the ideal situation. Okay. For the ideal situation, we need as less current as possible through this branch of the current circuit, and hence we will connect a resistance of infinite resistor of infinite resistance. Okay. So for an ideal voltmeter, how do we make ideal voltmeter? We make ideal voltmeter by connecting a resistor of infinite resistance in series with the given galvanometer. Okay. And what is the effective resistance of the galvanometer? Very simple. Here we have it, G plus R, right? So this is about converting galvanometer into voltmeter. Okay, pretty simple. You can compare galvanometer and voltmeter and understand the things. Okay, and math part is also important. Right. So this is the last session. Then the next session we'll discuss few formulae regarding the chapter moving charges and magnetism, and then we'll enter numericals. Okay. Thank you.